So today we will start with terminal velocity. Now this is basically subject we will be covering about friction. We are still continuing with friction. Before we start, do you have any questions about friction? Well, this kind of works. So you can see the slides and some video. Now the question we will be dealing with today, remember. Efendim? Okay, I will close the video. I have full slides. Okay, so that is what we will be dealing with, the terminal velocity. Now the friction, we had said that, well, you all know that friction is something that opposes motion in the general sense. In the sense that it will try to prevent relative motion of friction. We see the friction forces between solids. Now when we have liquids or gases, there's also some kind of a friction force. It's a friction force in the sense that it tries to prevent the motion. It's called the drag force. Now, our experience with the drag force. What do we know about the drag force? First of all, if I'm standing here, I don't feel any force due to the air around me. There's no friction force. So the drag force, let's call it F drag. This is equal to 0 if V is equal to 0. Now, if I start moving, I start feeling a very small breeze in my face. If I go faster, if you go in a car and put your hand out of the window of the car, you will feel a very strong force. So it increases with the velocity. Now, how it changes with the velocity, the magnitude of the drag force. With velocity, well, we know that for very small drag forces, it will be very small speeds, it will be 0, almost 0. If you start increasing the velocity, it will increase, but it might make any kind of funny behavior for very large speeds. But what we will be interested in is, if you look at very close to this region, it is almost a line. If we denote the slope of this line by some constant, the drag force, the magnitude is, well, this is the slope of this line times the speed. Well, it's a vectorial equation. It tries to prevent the motion. So it's in the opposite direction of the velocity. So this is its behavior for small velocities. If you go to larger velocities, of course, you can have terms like CV, V bar, plus D, V squared, V, all the higher terms. But for very small velocities, this will be enough for us. So if that is our, yes, some constant. Well, what does it depend on? What can you say? From your everyday experience. It doesn't depend on speed. No, it doesn't depend on the velocity. You see, the dependence on velocity is here already. So this is just a constant. You are talking about B. So what can B depend on? This is the friction. Kind of media. Medium. Well, you know that if you are moving in air, the force you will feel is very small. if you take a spoon and try to move it in honey at room temperature, you need to apply a very larger force. So it will depend on the media that you are moving in. What else? Size of the body. Does it depend on the size of the body? How? Yeah, it will have some dependence on the size of the body. But let me ask you this question. Again, you can experiment this. Just the next time you go in a car, put your hand out. Be careful that there is not much traffic. If you put your hand like this, or you put your hand like this, so the size of my hand doesn't really change. The size is same. So, but the friction, this drag force will change. So it doesn't really depend on the size of the body. Or if you put your hand outside and put something behind it, you are effectively increasing the size of your object. So, although you are increasing the size, the drag force will not change. So it doesn't really depend on the size. Cross-sectional area. These are the things that it will depend on. The cross-sectional area and the type of the medium. It depends on the speed. Because for higher speeds, you need, in the sense that for higher speeds, you need to include more terms in your expansion. But for small speeds, this will be enough for us. Okay, so now we have a force. Yes? We will come to that. We didn't yet come there. Word, you mean? I mean, if you have problem with the English of the word, just ask me. I can just tell it. Well, I haven't yet come to that slide. I will come to that. Oh, this is the, by the way. Okay, now I'm in this slide. So now we have a different kind of force that will affect the motion of the objects. Maybe very slightly. I mean, the force that well, terminal velocity, we didn't see that. You mean if you open your hands, there will be less drag force? Probably not. It will probably change it a bit, but not much. Yes, cross-section didn't change, so the drag force will not change significantly. It will change a bit. Because the issue there is if you put your hand like this or hand like this, you will feel a change in the force. But the main difference is that as your hand moves in air or in some liquid, your hand will also be carrying part of the liquid or the gas itself. So effective cross-sectional area is increasing because you are carrying with yourself more than what your hand is. So there will be some dependence, but not much. Now, so we have this force. Now let's go back to our previous question where we ignored air resistance. Just free fall, one example. We have a, let's say, a tall building, and we just drop some mass from here. Now, it's a one-dimensional problem. So you can just say that, okay, this is the positive z direction, but I will not be putting the vector signs. You should understand that whatever I write here is the component along the z direction. So it feels a force due to gravity. This is the gravitational force, mg. It also feels a drag force, mv. It is in the, if it's mv. If the velocity is positive, it is in the negative direction. If the velocity is negative, it will be in the positive direction. So this already takes into, it's against the velocity. This is the net force acting on my system. Sorry, this is BV. This is the net force acting on my system. This should be equal to mass times the acceleration. which I can write as acceleration is the mass times the rate of change of the velocity with respect to time. So we have this such a differential equation. Now, this is what an equation which is easy to solve. We will solve it, but before solving it, let's just look at what does this differential equation tell us about the behavior of my object. Now, first of all, we can consider the case that we leave it from rest. Initially, the object is rest. We just drop it. Since at first it is at rest, v is 0. So the acceleration of my object is nothing but the gravitational acceleration. So the speed increases. But as the speed increases, now let me at the same time drop the speed versus time. Accelerated. So initially it is moving, the velocity is increasing with the speed is increasing with time. The slope is determined by g. But then, since v is larger, the net force acting on my mass is smaller. But since the net force acting on my mass is smaller than its weight, its acceleration will be smaller than g. It got even faster. As this v is increasing, the net is decreasing. So the acceleration is constantly decreasing as the object is increasing. So initially it will move like this, then like this. Then it will accelerate with a smaller acceleration, smaller acceleration. Now, of course, it will not be like this, a curve of broken lines. It will be continuous. So this is how it will behave. It will increase. Since we are starting from at rest, it will always have some positive acceleration. But the acceleration will get smaller and smaller as the speed is increasing and increasing. Now, eventually, the acceleration will be almost 0. Now, the acceleration will be 0 when mg minus bv t is the velocity. This is what I define as the terminal velocity, the terminal Hız. When the velocity is such that this is equal to 0, it just means that there is no acceleration. Once the speed reaches this point, there will be no acceleration. And since there is no acceleration, the speed will not be changing after that point. My object accelerates until this speed, but once it reaches that speed, it will just move with the same velocity for the rest of the motion. So the terminal velocity, in terms of these parameters, is mg over b. Is it? Yes, this is the limit speed. This is the limit that the speed of the object that is dropped from rest will obtain. This is the limit of their speed. By the way, this is the speed that you owe your life to. Great. Okay, we will do that. That's great. Whenever you have a result, you should always do dimensional analysis to check whether your result is correct or not. Of course, here the first question is, what is the dimension of B? How we define B? The force is equal to minus BV. So B is equal to minus F over V. So the unit of B, the unit of force is newtons per meters per second, or Newton second per meter. This is the unit of B. Now let us check what is the unit of this mg over b. It should have the velocity of meter per second if we did everything correctly, but it will tell us whether we did some mistake or not. The unit of mg over b. The unit of mass is kilogram. The unit of g, meters per second squared. The inverse unit of p, which we have over there, it is meters per second. Newton has kilogram What's the unit of Newton? Kilogram meters per second squared. Newton is mass times the acceleration. MA. Kilogram meters per second squared. Well, we have the meters per second squared, they cancel. Kilograms, they cancel. So the unit of mg over b is meters per second. So probably we didn't do any mistake in the calculation. Now, any questions up to this point? So this is what we mean by the terminal velocity. You owe your life to this fact that there is a terminal velocity, because imagine the clouds are quite high. They are like 8 kilometers above, 8, 10 kilometers, depending on the kind of cloud you have. And the raindrops, they start from the clouds. So they go 8 kilometers, and when they fall on the ground, their velocity is not that much. They reach their terminal velocity and they stop accelerating. If they kept on accelerating, they would be enough to kill or damage you. So since there is this terminal velocity, you are able to enjoy the rain and go go singing in the rain. Now, any questions in this terminal velocity? What do we mean by the terminal velocity? Yes. We will do that. We will solve for the velocity as a function of time. But yes, we will find that function. But for the time being, we just analyze what this differential equation is telling us about the motion in general. We will become more quantitative. Now, this is what happens if we start from at rest. We know that the object accelerates until it reaches the terminal velocity. Now, the other extreme is if you just throw the object with a very fast velocity, very fast speed, very large speed, such that initially its speed is larger than this terminal velocity. Suppose you are here. At t equal to 0, the speed of your object is here. This is your initial condition. Now, in that case, we know that v is larger than this terminal velocity. V is so large, so this is negative. So initially the velocity is positive, the speed is positive. So the object decelerates, the speed gets lower. But as the speed gets smaller, this number becomes larger because it is negative, but smaller in magnitude because the velocity is approaching the terminal velocity, which makes this 0. So the speed got smaller. It will keep on decelerating with a smaller deceleration. It's still decelerating. Its speed will get lower. It will get closer to the terminal speed, but with even smaller acceleration. So this will be how it will behave. Again, it will not go below the terminal velocity, because once it reaches the terminal velocity, its speed will remain constant because the acceleration is 0 at the terminal velocity. So this we know how the speed of my object behaves in the presence of a drag force. This one. Now, to see that, let me write this in another form. Let me take this into a parenthesis of b. This is equal to minus b, v minus mg over b. This is the net force acting on my object. I'm saying that initially, the speed is much larger than the terminal velocity. So this is my terminal velocity, mg over b. Since the speed is larger than the terminal velocity, this number here is positive. I'm multiplying it with a negative number, so the acceleration is negative. So it is decreasing. I started here, so the speed is slowing down. At the next moment that I measure its acceleration, I will be here. It has some velocity, some speed. Now its speed is now closer to the terminal velocity. So this speed is closer to this one. So this number is smaller. It is still negative. It is still decelerating, but the acceleration is smaller now. So the slope will be more flat. So after this point, it will still continue decelerating. The speed will keep going down, but it will be more horizontal because the acceleration is smaller. The change in the velocity in a given time is smaller. So it will just behave like this. It will not continue decelerating with the same acceleration. It will decelerate with a smaller acceleration. Now I'm here. I have a speed that is even closer to the terminal velocity. So this parenthesis over here is even smaller. So its deceleration is even slower. So it will behave like this. It will not continue with this acceleration. It will have a smaller acceleration, a smaller deceleration, and so on. So instead of continuing like this, it will go like this. And, well, it will follow this curve. This is what we expect the behavior should be. Is it clearer now? Yes. This one. Well, if you talk about the magnitudes, in both of these cases, the magnitude of acceleration is decreasing. Because in both cases, the speed is approaching the terminal velocity, so the acceleration is going to 0 in both cases. But here we have a positive acceleration, so it is decreasing, it is getting closer to 0. Here I have a negative acceleration. It is increasing because it is getting closer to 0. Here I started with -5 meters per second squared, then I will, in the next moment, I will have -3 meters per second squared. Well, -3 is larger than -5. So the acceleration is increasing here. But its magnitude is decreasing. It goes from -5 to -3. The magnitude goes from 5 to 3. So this is just a qualitative description of how my object will behave if there is such a drag force. Okay, it is good to know the qualitative behavior as a physicist, but we are also supposed to be more quantitative about that. What will be its speed at this time? We have to be able to tell that. Now let's try to find the velocity as a function of time. Now here we will have the integrations that you love. Yes? When the starting point, this is my terminal velocity. In one case I started from a speed lower than the terminal velocity. In the other case I started with a speed higher than the terminal velocity. In this case, I just hold my hand out of the skyscraper and just release it. In this case, I just hold it and throw it down. So this is my equation. mg minus bv is equal to m dv by dt. Now, let's just first remember what this dv by dt means. I just take two successive time intervals, time points, a very small time interval, the length of which is dt, and I measure the change in my speed between these two time intervals, and the change in the speed I denote by dv. So this, what I write here, is actually the ratio of two very small numbers. So I can just treat them as if they are algebraic quantities. So if this is equal to mg minus bv divided by m, then I know that dv over g minus b over m v is equal to dt. Well, I have this curve. Let me just draw a typical the velocity as a function of time curve. I have this curve. I don't really know what is the curve yet, but I just take these two successive times. The difference in time is dt, and corresponding to that time change, I have a change in the velocity called dv. And this dv and this dt is related by this one. The change in time is related to the change in velocity through this relation. Well, the next thing I would like to do is just sum all these changes. So if initially I have, this is my initial time, t initial, I have the initial velocity, v initial. I will just sum dt, another dt. I will just sum all these time intervals until I reach the time t. And then, of course, the velocity will change by little, but the changes in the velocity will always be related to the change of time in this expression. Just summing up all these changes is what we call the integration. Now, as time goes from t initial to the final time, let's call it t. This is t initial. I know that, well, if I'm summing something on this side, I should sum the same thing on the other side so that to keep the equalities. So the velocity at time t equal to t initial, I'm here. This is the initial velocity, initial speed. And at time t, my speed is not, my velocity is v of t. So this equality should also hold. If it holds for each one of the terms I'm summing, then the sum is also equal to each other. The next is just integrate these things. If I integrate dt, it just gives me the t minus t initial. dt from t initial to t is equal to t minus t initial. This is the right-hand side. If I integrate the left-hand side, g minus b over m, v from v initial to v at time t. So, are you familiar with this integral? Are you familiar with the logarithm? Logarithm function? So, who is familiar with the logarithm function? Logarithm of x. Logarithm to some base b of x. I want to see more hands. I know more of you are familiar with this logarithm function. Who is not familiar with this logarithm function? So the rest of you do not know whether you are familiar or not. Okay, at least some of you are familiar, yes. You should have seen this logarithm function in high school. You might not remember it. Now, it has some nice properties which you will see this logarithm function throughout your physics career, whether you are from the physics department or physics education. What we will be interested in is we have this nice number, what we call the E, 2.7 and something. Almost always we will be dealing with the logarithm to this base E, which we call it the natural logarithm. We do not specify, instead of log, we just use ln. Now, the properties of this logarithm function is, if you have the product of two logarithms, then it is the sum of the logarithm of these two numbers. This you need to know. If you multiply the logarithm by some number, n, this is the same thing as the logarithm of x to the power n. And the last thing, if logarithm of x is equal to y, then x is equal to e to the power y. Logarithm is kind of the inverse of the exponential. These things you are, I'm assuming from now on that you know. This is what all the things that we will use. And in terms of integration, it also has the nice properties. Logarithm of x is the integral of dx over x. let me call it dy over y from 1 to x. So this is your logarithm function. You need to make a change of variables in the integration to bring this one into this form. But this, if you integrate it, this will be 1 over minus p over m. You see, logarithm of x is in a sense the integral of 1 over y. So the derivative of the logarithm of x is 1 over x. This is all we need about the logarithms. So if you come back to here, the integral of this one, this is VE. 1 over minus b over m, logarithm of g minus b over m v, where v goes from the initial velocity to the velocity at time t. Well, this symbol, it just means that if you want to calculate that integral, this is equal to minus m over b times the logarithm g minus b over m. So first, instead of b, we use the v of t minus the lower limit logarithm of g minus b over m v. The v is equal to the initial velocity. So t minus t initial should be given by this expression over here. Yes? Not this one. The previous one. Yes? In Turkish. So what we are... Okay, so just a repetition in Turkish, a fast one of what I have said. Şimdi şuraya bakarsanız dv bölü dt iki sayının oranı. İki sayının oranı şuna eşitse o zaman dv'nin mdv'nin mg eksi bv'ye oranı da dt'ye eşittir. Yani zamandaki değişim ve hızdaki değişim bu şekilde bir ilişkisi olması lazım. İçler dışlar çarpımı yaptım. İki tarafı da toplarsam, çok küçük değişimlerin iki tarafını da toplarsam toplamlar da eşit olacak. Çok küçük aralıkların toplamı da integral. And that is how we come to, so this is what we have. I'm just summing these very small increments, these very small numbers from both sides. And I'm having this integral over here. I forgot a factor of m here. Now, for the time being, it will be enough for me if you leave it in this form as integrals. I do expect you to know what integration means as just a summation over very small quantities. Well, if you do this step also, carry out this integration, that is even better. If you don't do it, you will not lose much. You will lose some. Yes, there was a question. A bit louder. The integral, this one. Sorry? In Turkish, again, the same thing? Well, which language do you want? I explained in English, no way. In Turkish, you still ask me one more? Well, I don't speak German. I can try the Spanish one, if you want, but... Let's look at here. In Turkish. Now, I will explain. Okay, so just ask your friend. So, who didn't understand this one? So, everybody, except you, everybody understood. So, ask some other guy, some other friend from the class. Sorry? You should, and tell me if they don't answer you. I will deduce points from them because they didn't tell me that they didn't understand. Yes. That is the definition. Okay, hold on. Back to this integral. Okay, I will not tell how to take this integral. I will pass this question, but in one of the recitation hours, you have a recitation hour today, right? Okay, you, at what time was it? At 5. Ask it in the recitation next week. How to take integrals, simple integrals. Now, for the time being, for me, it's more important that you get up to this point. And then write it like this, the first line, not the second line. Any questions up to this line? A bit louder. No, this is also the base e. It is the natural logarithm. Well, almost always we use the e base, so we don't really specify it. Another? This one and that one, they are the same. There is this one. M over B. M over B. Remember, use this result, this one over logarithm of x plus the logarithm of y is the logarithm of the product. So I just combine these two logarithms to get this one. Why I get the division? Because I have a factor minus 1 over here, which converts this to 1 over that one. Okay? Now, if you take this one, divide the numerator and denominator by m, you have this logarithms. In this one, there is this m over here. I have the m over here. This is also ln. This is not the logarithm. This is ln. Yes. We are always working with natural logarithms. Base is always e. This 2.7 thing. Your question again. Okay. Okay, I can combine these two logarithms and write the logarithm of g minus b over m vt divided by g minus b over m ve. Do you agree with this much? I multiply the numerator by m, the denominator by m. And this is what I would get. Now it's time for a break. So do you have... It is time for a break, but we are not yet going for a break. Any other last minute questions? So then before you go, I will explain how to take this integral in the last 5 minutes. So if you don't want to listen to how to take this integral, you can go for a break. So what we are trying to integrate, but if you would like to talk, please go out first and then talk outside. So this is the integral we would like to calculate. From the initial velocity to the velocity at time t. I first make a change of variables. So what I do is g minus b over mv. Let me just call it x. It is just a change of variable. Instead of my variable b that I'm summing over, I'm just defining a new variable x, which is not the position, just a different variable, so that it will get quite simple. Now, if I change v, remember here I have a change in the v. First, I need to determine how a change in the v corresponds to a change in x. But this is just a linear expression, so if I just take the what we call the first derivative, or let's say let me take the derivative of both sides with respect to x. Arkadaşlar konuşmak istiyorsanız dışarı çıkabilirsiniz. Burada tutmuyorum sizi. Ama burada olacaksanız da konuşmazsanız sevinirim. So I just I need to relate the change in v to the change in x. I take the derivative of both sides with respect to x. This is one thing that we can do. Now g is just a constant, it doesn't change with x. Minus b over m is just constant. dv over dx is equal to 1. Or I can say that dv is equal to minus m over b dx. So a change in v is related to a change in x by this coefficient over here. Now, if you go back over to this expression, this will be equal to, well, instead of the change in v, I can just substitute this expression. They are the same thing. So it's minus m over b dx. This factor over here is nothing but x. We define this whole thing as x over x. Now the other thing is v is changing from v initial. Well, let me write it again. The x, this is the definition of x, g minus b over m v. So as v goes from the initial velocity to the velocity at time t, x will change from g minus b over m ve up to g minus b over m velocity at time t. This is how x will change. Or this is equal to minus m over b g minus b over m ve g minus b over m vt dx over x. Now the integral of dx over x is nothing but the logarithm of x. That is how we define the logarithm function. It is equal to minus m over b logarithm of x as x changes from g minus b over m ve up to g minus b over m v. This is ve, the initial velocity, the velocity at time t. And this is what I wrote over here. This notation just means that first, instead of x, put this value minus this expression, but take x equal to this value. This is what I have over here. This is the result of, and from this equation you can solve for v of t. V of t will have such a complicated expression. This is our velocity as a function of time in terms of the initial velocity and the terminal velocity. This vt is the terminal velocity.